which is a matrix equation on the spinor field, which contains 4×4 Dirac matrices. So they're called either Dirac matrices or just gamma matrices. And they're defined by anti-commutation relations of this form. So they anti-commute on a unit matrix proportional to G mu. So what this equation tells us is that, so if you write it in components, you'll see that gammas with different indices anti-commute. So you can permute them with changing the sign. If indices are the same, then this is just an equation for the square of the corresponding matrix. So gamma 0 squares to 1, and gamma with the spatial index square to -1. So this is the context of content of this equation. And then, so there is this object psi, which is a spinor, and I feel that there was some confusion about what spinors really are. So let me try to describe this sort of in more detail. So spinors as vectors, they are characterized by the way they transform under Lorentz transformation. So first of all, spinor is a Coulomb with 4 components. However, you shouldn't confuse it with a vector, which is also, you can think of as a Coulomb with 4 components. So the psi has 4 indices on which gamma matrices act. Now, the way, what makes it different is the way it transforms under changes of this coordinate systems. So if we make a Lorentz transformation, which is just a change of variables in the way that we map the space-time by coordinate system, then, okay, we know that vectors transform with the same lambda. So this equation is a definition of what we call vector. This is a definition of a vector. Right? So anything that transforms like that is a vector. Now spinors are transforming with a different matrix that we defined by L. And this L is a function of lambda. So to find L given a lambda, we need to solve the following equation. So this equation determines lambda as a function of L. It determines what I'm saying. It determines L as a function of lambda. And so in the previous lecture, I've started to describe how to solve this equation, how to find L given the lambda. Okay, but now suppose that we solve this equation and we for any lambda we know what is L, then the definition of a spinor is that spinor is a four-component object that transforms by left multiplication with L. So I write this with all the indices explicitly written just for you to see, but usually I'll skip the indices on spinors. So this is the defining equation for a spinor. In other words, spinors are four-component objects that transform under Lorentz transformations, whose rule of transformation under Lorentz boosts and rotations is given by this formula, or by these two formulas. So as a first step, we should compute L, and then, okay, we know how L will look in another different frame. Yes?
Where does equation start from? Why does that determine L in terms of lambda?
Well, this is just a definition. So I give you this as a definition. Why this definition is useful should become clear from the following two statements. So the first statement, in which
So why do you define L rather than L?
well, because at this point is a matter of convention. So if I write it as L minus 1, then here I should also write L minus 1. But I want to determine, I want this to be called L, and then it should appear precisely as written. So let me leave checking of this property as an exercise. Namely, you may want to check using the defining property of lambda that Lorentz transformations leave the Dirac equation invariant. So it's a simple exercise, but a useful one to do. So I suggest that you do it yourself later. So this is one property that tells us why this definition is useful. The second property is that this definition makes L a representation of the Lorentz group. So you know that transformations of coordinates that leave the Minkowski metric invariant, they form a Lorentz group, a group which is called the Lorentz group. So if you apply two transformations to X, it will be another Lorentz transformation, and so on. So to check that L formed a representation of the Lorentz group, we need the following conditions to be satisfied. So if you take product of two L's corresponding to two Lorentz transformations, this should be equivalent to L evaluated for the combined transformation that's a product of lambda 1 and lambda 2. Then L of the inverse transformation should be equal to inverse of L. And finally, L of the unit transformation should be just a unit matrix. So these properties ensure that L defines a representation of the Lorentz group. Which obviously is called the Spinor representation. Actually, it's called bi-Spinor representation. So checking these three properties is really easy. You just apply two transformations here and check that the product of L satisfies, again, the equation for the product of lambdas. The taking inverse of lambda here is the same as taking an inverse of L. This should be also easy to show. And of course, if lambda is 1, then L is obviously 1. So spinors form a representation of the Lorentz group, which is distinct from the vector representation. But okay, they since the spinor representation is there, of course, there can be fields that transform in this representation, and these are the spinor, the Dirac fields. Now, we started to explicitly construct what is L in terms of lambda. So we will only do this for infinitesimally small Lorentz transformations, where it's easy to write explicit expressions. So infinitesimal Lorentz transformations, meaning that they are very close to the identity transformation, are characterized by a set of parameters which form an antisymmetric tensor. So roughly speaking, this tells us in which plane the rotation takes place, right? So it has two indices. It characterizes the plane of rotation, or if one of the indices is the time index, it tells us that we are doing a boost in the direction that is given by the second index. But in principle, this is a numeric matrix. So if you lower one of the indices, this must be a numeric matrix, which is antisymmetric. So then we can use this property, which tells us that for the identity transformation L is 1. So for transformations close to the identity, L should be equal to 1 plus something small. And so it should be linear in this omega. So in general, we can write it in this form. So it starts linear with omega, and then there are some nonlinear terms. But as usual in group theory, it's enough to understand the linear part of the transformation rules. The nonlinear part will is reconstructed by group theory. So it's enough to understand how the Lie algebra is represented to understand the representation of the Lie group. Anyway, so what we want to achieve here is we want to substitute this for L in the equation, linearize in omega. Then we equate left-hand side and the right-hand side. And at the end, it boils down to an equation for the sigma that should have some prescribed commutation relations with the Dirac matrices. So this just follows from the defining equation of the Lorentz transformations acting on spinors. Any questions here? So is it more or less clear what is the difference between spinors and vectors and what spinors are and how they transform? Okay, then I'll continue with, so this is sort of a just definitions, but now let's continue and solve this equation and find that indeed, so in a sense, the consistency of all these constructions is based on the fact that we can write down explicitly what are the sigmas in terms of 4x4 matrices. Yes.
This year we didn't have a chance to see Lie algebra in the front end of our course. So would you mind showing how you got that equation for L equals 1? I mean, apart from the 1.
Oh, okay. So this is, well, it's, you don't need to know any Lie algebra theory. You just substitute this equation to the equation star. Right, so you have, forgetting about the nonlinear terms. So it should be correct order by order in omega, in particular to the linear order in omega, it should be satisfied. So what we get is an equation of this form. So 1 plus, let me write it symbolically, sigma. So this is minus 1. Gamma 1 plus 1/2 omega sigma equals to lambda gamma. Okay. So then this is the leading linear order is 1 minus omega sigma. So then for lambda you should substitute delta plus omega. And then you equate terms of the same order in omega. So the first term is just gamma equals gamma. And then the linear term in omega is, on the left-hand side, this is 1/2 omega minus sigma gamma plus gamma sigma. And on the right-hand side, you get just omega gamma. And then you just equate this coefficient in front of the gamma on the left-hand side to the coefficient of the gamma on the right-hand side. And if you do it accurately with all the indices explicitly written down, you just get this equation.
I'm sorry, I probably didn't express myself clearly. The answer is, why do we expand L as that sum?
Well, so L is some function of omega. Okay? So then omega, sorry, L is a function of lambda. And lambda is, well, unit matrix plus omega. So then we just Taylor expand, so L of 1 is 1 because of one of these properties. And then here we can write it as omega times sigma, where sigma is just a derivative of L with respect to omega.
I'm just confused because I'm used to seeing in a Taylor extension that the 1/2 is associated with the second derivative times.
Then 1/2 of omega is the derivative of L with respect to lambda. So this is just a definition of what omega is. We have chosen to normalize it with a 1/2.
Thank you.
Could have written 1/4 here, but then 2 will appear in this equation. So it's just a matter of convenience. Any other questions about all these formulas? Okay, very good. So so then the claim is that there is a solution to these equations that is just the commutator of Dirac matrices themselves. So using Dirac matrices, it is possible to construct the sigma matrix. So the Dirac matrices, we know that matrices, so there is a defining equation here, but there is also an explicit formula for them and as numeric 4x4 matrices. You just take this formula, substitute for the gammas in the commutator, and then we get the sigma. And so this tells us how rotations and Lorentz boosts act on the spinors. So, well, let us first check that this equation is correct. So we need to compute a double commutator of 3 Dirac matrices. So we should take a commutator of gamma nu, gamma lambda, and gamma mu. And this should be linear in gammas. Now, so one way to do it would be to take 4x4 matrices, plug this in Mathematica, and it will, in a second, produce some metrics that you should identify with the right-hand side. But usually, with the Dirac matrices, you never, or almost never, need to know what is their explicit form as matrices. It's just enough to know how they anti-commute. So the defining relation for them that the anti-commute on the unit matrix with the coefficients that are the metric tensor is sufficient to do almost any calculation with the Dirac matrices, or in other words, in meaningful calculations, everything can be done just with this, just using the anti-commutation relations. So in particular here, it's a good example to see how the Dirac algebra works. And so let's go through this calculation explicitly. So this is a well, double anti-commutator. So it's a combination of 4 terms of gamma nu, gamma lambda, gamma mu, minus gamma lambda, gamma nu, gamma mu. So this is the commutator of the first 2 entries. And then there will be we should put gamma in the first place, gamma nu gamma lambda plus gamma nu gamma lambda gamma nu. So then, to simplify this expression, I then combine terms differently. So first so in this commutator formula, these two terms sort of have the same origin. So this is a commutator of the first two Dirac matrices. But let me combine them differently. So let me combine these two terms and these two terms. And you see that they have the same structure in the sense that here we have a product of two Dirac matrices, and then the third matrix appears on the right and on the left. Here they multiplied, two first entries multiplied in a different order, but then again gamma mu appears once on the left and once on the right. So what we need to do is we need to take a triple product of gammas and somehow simplify it. And so what we want to do is we want to bring this expression to the form where it is equivalent to this one, so the gamma mu stands in front instead of standing in the back. So the anti-commutation relations allow us to do it because we can anti-commute gamma through any chain of other Dirac matrices. So for instance, here we can write this as gamma nu, and then replace a product by anti-commutator, gamma lambda, gamma mu. But of course, an anti-commutator has two entries in it, and so we should subtract the one that doesn't appear on the left-hand side. So this term is just a C number, so it is equal to 2 times G lambda mu gamma nu. And then the second term, gamma, is shifted one position to the left. So now we repeat the same procedure. We shifted again, we anti-commuted through the gamma nu. So what we'll get is minus the anti-commutator gamma nu with gamma mu, multiplying gamma lambda, and plus gamma mu gamma nu gamma lambda. So what we got is that there are two anti-commutator terms which contain less gamma matrices because anti-commutator of two Dirac matrices is a C number. And then the term where gamma is now appears on the left of gamma nu gamma lambda. So you see that here in this expression, this term will cancel with this. And so we will only get the linear terms in the gammas. Now, these two terms combined will only differ by interchanging indices lambda and nu. But this expression is anti-symmetric in lambda and nu anyway. So the result will be just twice this anti-commutator part. In other words, this double commutator is equal to 4 times G lambda mu gamma nu minus 4 G nu mu gamma lambda. And if we divide by 4, then we get the equation that we wanted to prove. So this is a very typical calculation for gamma matrices. You always, in all the calculations that appear in field theory of, well, Dirac fermions is of this type. Okay, so in principle, this constructs the Lorentz transformations for spinors to the linear order in the transformation parameter. Now, since this will be enough for us, I will not extend it to higher orders. But in principle, one can construct them well, explicitly. So one can reconstruct the whole function L as a function of lambda. I will not talk about that because it's a bit technical, and we will not use it later in the course. But actually, there is a funny property of spinors that so these spinor transformations, they actually they have some funny properties. For instance, if you rotate a vector by 180 degrees, it will go back to itself, right? So if you rotate something by, 180 degrees, it's equivalent to doing nothing to it. But for spinors, yes, 360. So 360 degrees rotation is equivalent to a unit transformation, but not for spinors. For spinors, 360 degrees transformations multiplies them by -1. And so trivial transformations require rotations by 360 degrees twice. So that you can sort of understand from the defining equation for the lambda, because in this equation, lambda enters quadratically, but L enters quadratically, but lambda enters linearly. So for any lambda, there will be two solutions that differ by multiplying L by -1, right? So we can multiply L by -1, and it will still solve the equation. So in fact, spinors represent Lorentz transformations. So there are two spinor transformations corresponding to one and the same transformation of vectors. So spinors, they know a little bit more about rotations. They transform in a more refined way. And as a result, the transformation by 360 degrees is not an identity. But that's sort of a detail that will never resurface again in field theory. What will though be important for us is the relationship between the Lorentz transformations and the spin. So the claim is that the difference between spinors and well, scalars that don't transform at all will result in the appearance of a spin of the particles that described by the Dirac equation. So how to see this? Well, spin is I mean, somehow in ordinary courses of quantum mechanics, they talk about spins, but manage to do it without talking about rotations and about rotations. Whereas the spin is actually a property of a system with respect to rotations or to Lorentz transformations. And so let me try to emphasize this relationship in the context of field theory. So we'll first try to answer a question: what is angular momentum? A spin is obviously part of an angular momentum, so we need to understand how do we think of angular momentum in field theory. Well, in mechanics, angular momentum is just a vector as a product of x and the linear momentum with the cross is a cross product of x and p. So if something rotates around axis n with angular velocity v, then the angular momentum will be directed along this axis and will have the amplitude that's proportional to the angular velocity. It's as simple as that. Now, I don't know if you appreciated this fact, but the description of rotation with a vector is very specific to the fact that we live in 3 dimensions. So if you imagine rotation, so suppose that there is some fourth dimension of space. Then rotation characterizing rotations with a vector will not be possible. Just because if you suppose that something rotates in a given plane, then there will be actually 2 vectors that are perpendicular to this plane, right? So a better characterization of rotation is actually to characterize it not by a vector, but by a plane of rotation. So that would be true in any number of dimensions. It is just in 3 dimensions that we can characterize a plane by a normal vector, by a vector that is normal to it. So in 4 dimensions, that's not true anymore. So a better way of thinking about angular momentum is that it's not really a vector, but rather a tensor with 2 indices that characterize the plane in which rotation takes place. So indeed, if you write this formula explicitly in terms of indices, and well, we will switch to the quantum mechanical notations where P is d over dx. Then the angular momentum operator is, well, is given by product of x and p, and then contracted with the epsilon symbol. So we can equally well characterize it by just this product without the epsilon symbol, but of course what epsilon symbol does, it antisymmetrizes in indices j and k. So we could characterize it by a tensor Lij, which is define it as epsilon ijk contracted with Lk, and this is simply not right half. So this will be then x I is j minus xj di. So we can call this operator an angular momentum. I mean, it's equivalent, of course, to this one, because they're related by contracting with the epsilon. But this formula can be readily generalized to the space-time picture when we have 4 dimensions. You just write mu and nu indices here, and this would be a relativistic angular momentum, relativistic counterpart of the angular momentum operator. So let us see how does it arise in field theory. And for that, we will study how Lorentz transformations act on, say, the Klein-Gordon field. Well, so if we do a Lorentz transformation on X, then the field will transform by the inverse transformation of its argument. Yes?
I'm sorry, but the angular momentum tensor, we're defining it on the 3-dimensional space? I mean, there's no time coordinate, right?
So far, no, but well, you'll see how it will arise in relativistic quantum, well, in relativistic theory. What I wanted to stress is that this formula we cannot possibly generalize to include the time index. But this sort of formula we can, because we just say we can easily define a tensor that whose spatial components will be Lij, and which is defined by, well, allowing these indices to vary from 0 to 3, right? It's a very simple generalization. But the step from here to here is only possible for spatial indices. There is no counterpart of this formula in 4-dimensional Minkowski space. So, so now, what is the content of these formulas? Well, should I explain this? Why do we write lambda minus 1 here, for instance?
Yes, explain.
Yes. Okay. So, so let's see. Let's consider translations instead of rotations. The idea is the same. So if we have 2 coordinate systems, one is the. So this formula just tells us how to go from one coordinate system in space-time to another. So we have an old coordinate system and a new coordinate system. And then there is some field profile that actually doesn't change. So you might think of this as, so suppose there is someone defined a landscape of this field phi. So it has some given shape as a function of a point in space-time. And then, so the way to go from this landscape to a function of x, we need to introduce the coordinates, right? So we draw a coordinate mesh in space-time, and then each point is assigned coordinates, and we can compute this function by evaluating the field at this point. So, and then we change our mesh, so by shifting it to the right. So the field itself will not change because of that, but the way we assign a function to describe this landscape given by phi will be different. So in the new coordinates, so to compute this function in the new coordinates, so this will be simply a different function. So suppose we want to compute it at this point, at the origin of the coordinate system. So what we do is so the new coordinates are shifted to the right by, say, by vector A. Okay. So what will be then the value of the of the field in the new coordinates? Say at this point. Suppose that we know this function in the old coordinates. Then, of course, in the old coordinates, what I'm trying to say. So, so what I'm trying to say is that that this function will be is the old function evaluated with the, we need to go back to the original coordinate system where this point was distance a from the origin, evaluate this function there, and then this will give us phi in the new coordinates. Okay? Sorry? No, this, so if you transform x.
The phi theta at 0 should be phi x plus x goes to x minus a. Shift it to the right.
So the claim is that if x nu is x plus a, phi nu of x, phi of x minus.
That should be x minus a because the new 0 is at old x equals to a.
Just a second.
That the new 0 is.
That was the, yeah, just, yes, you're right. So, you're right. So, I'm sorry, so here should be minus. To conform with this picture, here should be plus, here should be minus, and here a plus. So in other words, suppose we want to measure the field at this point. So the coordinate at this point, so in the new coordinates, this is 0. In the old coordinates, it was a. Okay? So to find the field at 0 in the new coordinates, we should evaluate it at a in the old coordinates. So the argument of phi goes in the opposite direction to compensate for this shift of the coordinates, okay? In other words, if we do some transformation on the coordinates, the argument of the phi will rotate back to just describe the same physical situation. I mean, I'm trying to say a very simple thing, but maybe in the words that are kind of confusing. Anyway, so if you have some function, then if you change x in some way and then apply the inverse transformation inside the argument, obviously the function will not change, right? So in other words, this is how the transformations will act on the field if we transform x to some new frame. So let us make a short break for 2 minutes.